I have a memory for that sort of thing. So anyway, since secant, y equals secant of x, is equal to 1 over cosine of x, secant is going to have a vertical asymptote, wherever, you know what, I don't even know I tried writing it like that. Anywhere cosine of x is equal to 0. All right, so let's imagine that the red graphs aren't there. And in fact, I can do more than imagine it. Go into your calculator and just turn them off. Hit enter on the equal sign and turn off an equation. All right, so here's my cosine graph. If I create a vertical asymptote everywhere there's a 0, because where cosine of x is equal to 0 would be the zeros of the function, hence the term, VA, so on. All of these would be vertical asymptotes. Infinite discontinuities, if you like fancier jargon. Now, we talked about this when we dealt with absolute value functions. What does an absolute value do to a number? It takes a negative, makes a positive. So why wouldn't it do the same thing to a graph, right? Okay, well, secant is a reciprocal of cosine. So why would that relationship be any different within the graph, right? So if I take in each interval the curve that's there and flip it, I'm actually taking the reciprocal of the graph. So that's how this graph comes into being. Same thing works with cosecant. Yeah, you draw the sine function, find all the zeros, draw asymptotes, and then just flip the relevant curve. But you have to flip it within the rules of the situation. Right? It has to also have an asymptote. So it means that not only are we flipping it, we're not going to terminate at 0. We're going to terminate at the opposite of 0, reciprocal of 0. 0 versus undefined. Right? Going from a slope equal to 0 to a slope of undefined, changing you from being horizontal to vertical, giving you a vertical asymptote. Right? So having a sense of these things is really nice because it gets you a little bit further along quicker. All right. So in terms of the graph, though, well, if I'm using the calculator, I mean, all that is like, okay, cool. I have a calculator. So I'll just do that. X equals 4. All right. So in my window, 0, x equals 4. X equals pi over 4. Pi over 4. Since we know that there are asymptotes, zoom fitting the y max or y min isn't going to cut it because it doesn't stop increasing. There's no max, there's no min. So you're dealing with something that is going to confuse the calculator. So this is the one exception. So secant, cosecant, tangent, cotangent, those types of graphs, the zoom fitting of the y min or max, it won't work the way we want it to. So we try -4 to 4 and see where we go. Just making sure there was no other function there that I'm missing. Okay. And graph. Right. That should have been fine. I'll do -10 to 10 just to syntax. Goto. Like that is a mistake I never make. But I did it this time. All right, zoom trig. I don't have it on? Oh. Well, thank you, because That was going to be a lengthy journey. Like, what is wrong with this thing? And then I would have gone on another diatribe about technology. Saved us all. All right, so I got this. It's very anticlimactic. But what we're looking at there, let me just paste it in. We're looking at just this tiny piece over here, just this little sliver here, right? I'll even highlight the relevant piece. That part of the secant graph. All right, so even if you know what a secant graph is, sometimes on a particular interval, you might need some help. So what I want to do is I want to create an arbitrary rectangle, and I want to rotate it about the x-axis. So I'm going to go like this. Oh, that last one took any possibility of this looking halfway decent and just destroyed it. I mean, it still looks terrible. I need to be... Try it this way. Say it again? I have no idea. I'll look in a second. It might be better for the best that nobody's hearing me say anything about this nonsense. It's all being recorded. Wonderful. So, that arbitrary rectangle is tracing a circular path around the x-axis. Right, so it's working its way around. But what's happening is we're going to get a shape that looks something like this. And then I'll just do a little... something along those lines. All right, but what it essentially means for us, and this is all we need it for, traffic drawing aside, is the idea that whatever the distance is from the x-axis out to the curve, that's going to represent the radius of the circular disk that I'm incapable of drawing. Right, so the model that we use for the disk method, again, is pi r squared d something. Depends on which way you're going. All right, so pi times whatever the r is squared. This one's getting revolved around the x-axis. So that arbitrary rectangle has a thickness that is in terms of x. All right, the height of the rectangle. So I'll just draw another one kind of off in space over here. That height is some distance y by dx. Y we know, because any point along this curve has a coordinate of x comma y, but specifically because it's on that curve, x comma secant x. So all of that is for the purpose of me saying that this should be secant x. They gave us the interval bounded by the axes, so that's 0, going out to pi over 4. This one you could figure out without a calculator, because secant squared has a known antiderivative. The problem is, if it's not known to you, it's not overly helpful. So, to the calculator we go. Pi times secant, so 1 over cosine x. Or you could use your y, I have it in y2, but you could use your y function to get it. Squared dx. So I close parentheses here for the cosine function, then I close parentheses again for the 1 over cosine. That's the only thing that should be squared. Everything else is remaining within the integral. So enter, and of course you get pi, because if it's something that you could do by hand, the odds were that we were going to get something that was recognizable. Pi over 2, something along those lines. Right, so that is the volume of that entire quasi-cylinder. Now, number 2 is my favorite kind of problem. Like really favorite, not favorite as in I'm hinting it'll be on the test or anything, but favorite as in I think it's pretty cool. All right, so it's an ellipse. So ellipses or ovals, they have symmetry about its particular axis. Right? And it's not always the x and y axes, but in a lot of cases it is. All right, so what we can do is we could figure out the x and y intercepts here and plot the ellipse that way, instead of actually having to recall everything that you should have known about conic sections for pre-calc, which is a lot. Find the y-intercept, put in a 0 for x and solve. 9y squared equals 9, so y squared equals 1. So my y-intercept would be plus or minus 1. For my x-intercepts, replacing y with 0, so it's the same as covering up the y term. X squared equals 9, so x is equal to plus or minus 3. All right, so there's my ellipse. Now, technically you can get, I mean, we're going to have to solve this for y in terms of x in a minute. So technically you can do that, put it in your calculator and take a look. But graphing by intercepts is one of my favorite ways to create a graph. It's usually pretty easy. And odds are at some point you have to come up with the intercepts anyway. So you're killing two birds with one stone. Anyway, we're spinning it around the x-axis. I don't like this formatting. I would like the x and the axis to be together. So if somebody wants to submit that for typo bonus, I'll take it. But I want to spin my arbitrary rectangle, which is going to have a thickness, I'm on fire tonight, a thickness of dx. I'm going to spin that around the axis. I'm not going to draw it because it's not going to look any better than the previous graph. But basically we're getting out of this the idea that this is going to give us the radius. Okay. Now the coordinates, again, of any point in space, coordinates are always x comma y. Because it's on this curve, it's x comma whatever y is, algebraically. We just got to figure that out. So then once we have that y value, that's what our r is going to be. R is the y value. All right. Now, you may be concerned about the curve on the bottom because the conic section is not a function because it fails the vertical line test. So we could integrate from -3 to 3. We can integrate from 0 to 3 and double it. But we absolutely do not have to worry about the bottom because when you spin this rectangle around the axis, it's going to pick up that curve on the way anyway. So we don't need to even consider this. In fact, all we need in order to figure out the final answer for something like this would just be the first quadrant. I just need this guy. That spun around the axis is all I need. All right? As long as I know what that curve is, I'm good to go. So I need to solve this for y in terms of x. So I'm going to subtract the x squared, divide by the 9, that's in front of the y squared, and then take the root of it. And that's what y is going to be equal to. So subtract, divide, and root. You can simplify if you want. I honestly don't really recommend it, because if you do and you screw it up, then you took a perfectly useful equation that the calculator can understand without any trouble whatsoever, and you made it incorrect. I wouldn't do that. I wouldn't take the chance. Because we all do weird things on test day. That, you do a problem 100 times, 99 times you don't make a mistake. The one time you do the problem and make a mistake is when it's on a test. Okay, so on the interval of -3 to 3, or you can go 0 to 3 and double it, pi times the radius squared dx. I left off the plus or minus because it's going to square away anyway. You square negative, it becomes positive. All right, so I'm just going to leave that off. Math 9, -3 to 3. Mode's irrelevant because there's no trig in it. Put a little radical. Well, actually, I could just put the expression without the radicals, so let me do that because it's going to square away. I think I hit the second key, so let me undo that. I'll just put the fraction in without the radical. So 9 minus x squared over 9. But again, during a test, maybe you put it in exactly as you see it for fear that you're going to make an inappropriate assumption. But this would be my volume. This would be the volume of the football. So I guess a 6-inch football, like one of the mini guys, has roughly a volume of about 12.6 cubic inches. I don't know. It could be a little football, but I don't know. By now, hopefully you're starting to like the questions that say write but do not evaluate an integral. Because as easy as it is to put in a calculator, it's just a pain. It's annoying. You don't want to do it. So let R be the region in the first quadrant bounded by these two graphs and the y-axis. So area and volume, mixing them up. First quadrant's all I care about. 2 radical x looks like this. Y equals 6 would look like this. To some extent, they'll have some kind of intersection. I don't know where that intersection is, but it'll have it. And we want to bound it with the y-axis, so I'll take this as a unique typo. I want the y and the axis together. All right. So, let me label. Zoom. 300%. Boom. All right, so I'm looking for this area in here. Now that entire interval, that entire region is bounded between this curve and the y-axis, making it most appropriate to have horizontally oriented arbitrary rectangles. So this is a dy situation, right? Because with a single integral, I can get from 0 to 6, and I'm only bounded by whatever this x distance is, dy. All right, so I just got to figure out what this x is. That's coming from this guy. So I need to solve for x. I'm going to divide both sides by 2 and then square it. So x would be equal to 1/4 y squared. All right, so y over 2, then you square it. So it becomes y over 4 squared. Or y squared over 4. All right, so I'm looking at an integral from 0 to 6, 1/4 y squared dy. So the orientation, or the change in perspective anyway, made our life a little easier, because if you didn't do it that way, what you would have to do is find the intersection here between these two curves to give you the outer bound for x. Then you'd have to integrate the difference between the dominant and the non-dominant function. So whatever the intersection is, let's see here, 9. I think this is 9. You'd have to go from 0 to 9, and then the integral would be 6 minus 2 root x dx. A little bit more than you need, because this is much simpler, right? Even if you have to put it in the calculator. And again, you could still put it in using x values, but I found that people tend to be a little bit more satisfied if they put it in with the y's, because it looks like it should. Nice area there, 18 units, square units. Which of course looks nothing like what I drew, but that's fine. So we want the solid of the volume of the solid generated when r is rotated about the line y equals 6. All right, so let's get that diagram again. This time we'll do it a little bit better. Going to exaggerate a little bit more. We'll have that intersection there. This is again y equals 2 root x. All right, so I'm spinning around this. Again, pi r squared d something. Going from something to something else. Well, arbitrary rectangle. If I want to spin the relevant region, the arbitrary rectangle would have to look something like this. And it would be getting spun around in this direction. Yeah, it sucks. I just can't. All right, well, whatever. It's a circle. It's trying to be a circle. I just can't draw. I'm more upset about this than you are, but I just can't do it. I see in my mind what I want to have on paper. I just can't make it happen. Anyway, this is the rectangle that I want to spin around, but that rectangle is not in contact with the x-axis. All right, so let me get rid of the nonsensical diagram that I drew and just focus on that rectangle for a second. Because what I need is the length of this whole thing. So I need that distance. Now I do know that going from here to here is 6 units. Going from use red. I'll use blue again. Going from here to here is y units. So if I want the distance in the middle, the height of that arbitrary rectangle, I'd have to subtract these two things, the 6 and the y. So this distance is 6 minus y. All right, so that's the length of the radius, 6 minus y. But we're integrating with respect to x because the thickness is an x measure. Even though it's not on the x-axis, that doesn't matter. It's still a horizontal infinitesimal change. And that's a change in x. So dx. So I need my bounds. I'm going from 0, start here, end here. All right, we get that intersection. I did it in my head before, but I could have been wrong, so let me just write it. The intersection would be 6 equals 2 root x. Divide, you get 3 equals root x. And so x would equal 9. Okay, so I didn't screw it up. Pi times 6 minus 2 times the square root of x squared dx. That's all they're asking for.